Hello everyone, I hope that you all are doing well. Today we will discuss a very interesting question, and this question is from the functional analysis part, and this question is asked in GATE 2025. Okay, here what is given? C alpha space is given. This is called the order continuous function space, and this is defined in this way. It is a mapping from the 0 1 closed interval to the R, and the condition is that f of t minus f of s modulus divided by t minus s modulus whole to the power alpha, the supreme value of this quantity should be finite, and this type of spaces are called the order continuous spaces, and here the exponent alpha strictly lie between 0 and 1. Okay, and this space is a Banach space, means it is a complete non-linear space, but with respect to this norm f of 0 plus this quantity, because we have already told that this quantity should be finite, so it is a well-defined norm. Okay, means this space c to the power alpha is a Banach space, means it is a complete non-linear space with respect to this alpha norm. Okay, and we know that the continuous function space c01 with respect to the sup norm is also a Banach space. Now we will in the question what is given, there is a map between the function space c to the power alpha to the c01. In this space the norm is this alpha norm. Okay, in the domain space there is alpha norm, but in the range or the codomain space the norm is with respect to the sup norm, and the map is the identity map. This one is the identity map, and question is about what, whether the map is a compact linear map or not. We have to verify this, and the image of t is a closed set. Image is nothing but image of t is what, image of t, because this is identity map, this is nothing but the c to the power alpha. Okay, alpha 01. We will check that whether this space is closed in this space or not, whether it is dense in this space or not. Okay, we will verify these things, and we will check that whether this map, identity map, is bounded linear map or not. Okay, first before going to verify these options, first let us discuss about some auxiliary results on the order continuous space. Means first we will check that this continuous function space and this order continuous function spaces are not same, and later we will verify that this order continuous function space lie in the continuous function space. Means order continuous function spaces is a subset of the continuous function space, but the continuous function space is not a subset of the order continuous function space. Means there is a continuous function space in this space which is a continuous, but it is not a order continuous, and this can be verified by using this standard result. This standard result says that the function f of x equal to x to the power beta, and beta lie between 0 to 1 is a C alpha order continuous if alpha is less than equal to this one. Okay, for if we take f of x equal to in the particular case, if one take alpha equal to half and beta equal to 1 by 3, then f of x equal to x to the power 1 by 3 is not c half 0 1. So this is a continuous function, but which is not half order continuous function. So this implies that c half 0 1 cannot be equal with the c01, because this f function lie in this space, but it does not lie in this space. Okay, means f does not belongs to this, but f belongs to this space. You can verify this standard result. It is a real analysis result, one can verify it. Okay, it is your homework. Okay, now the next task is to prove that C alpha is the subset of C01, but these two spaces are associated with different norms. C alpha is associated with the order continuous norm alpha norm, and this space is associated with this norm. Okay, the standard way to verify that, let we take an element in this space and we will show that it lie in this space. Okay, let f belongs to C alpha. I am not writing all the things C01 and norm alpha. Okay, then it implies what? F alpha norm is finite, means f alpha norm is defined in this way. It is f of 0 plus this supreme things. Okay, it is defined in this way. What? It is equal to f of 0 modulus plus supremum of s not equal to t and s still lie in 0 1 close interval, f of s minus f of t modulus divided by s minus t modulus is finite. This quantity is finite. This is given. Claim, what we are claiming? Our claim is to f belongs to C01 which is associated with the supremum norm. Okay, means we have to check that what we have to check, f is continuous plus supremum norm of f should be finite. These two things we have to verify. F continuity of f comes from this finiteness, because this quantity finiteness implies that supremum of s not equal to t, s comma t belongs to 0 1 f of s minus f of t modulus divided by s minus t less than some constant quantity c. Okay, finite means that we can find a positive constant quantity. This implies that f of s minus f of t mod less than equal to, here alpha I forgot to put an alpha, c times s minus t modulus alpha when s equal to, here s equal to t is also not a problem. When s equal to it is vanish and it is a non-negative quantity, so there is no problem for all s and t. For all s and t belongs to 0 1. Here it was not s equal to t, but here we can get s equal to t also, no problem. Okay, and this implies that f is a continuous function. Continuous. How? You can verify it, because if you take any epsilon less than, then you can find a delta which is nothing but epsilon by c. C is a positive quantity whole to the power 1 by alpha. If you sub s minus t is this one, s minus t modulus, by using the standard definition of the continuity you can show this is a continuous function. So continuity is not a problem. Let us check the second quantity. This norm should be finite. So to find this norm is defined in this way. F supremum, the norm, this is supremum of x belongs to 0 1 f of x modulus. So we will start from the modulus of f of x. We already know that f of 0 okay, let us start. Okay, we know that f of 0 modulus is less than equal to f c to the power, but this is obvious because in this definition of the alpha norm f of 0 is already there. So let x not equal to 0, x not equal to 0, then we will start from f of x modulus. We will calculate this one, and this can be bounded by using the triangle inequality, f of x minus f of 0 modulus plus f of 0. We will add and subtract f of 0, then we will apply triangle inequality. Okay, and this quantity now we will multiply and divide by x minus 0, and because x not equal to 0, we can multiply and divide f of x minus f of 0 modulus divided by x minus 0 modulus. X minus 0 modulus is nothing but x modulus, so it is x modulus plus f of 0 mod. Okay, these things, and here one thing is x belongs to 0 1 close interval. This implies that modulus of x is less than equal to 1. So this can be bounded by, this quantity can be ignored by using the bound 1. So it is f of x minus f of 0 divided by x minus 0 mod plus f of 0. this is modulus, and this quantity is dominated by supremum of s not equal to t, s t belongs to 0 1 close interval f of s minus f of t modulus divided by s minus t modulus plus f of 0, because in the particular this quantity contains so many elements, but here it is containing one element, because in the particular case if we take s equal to x and t equal to 0, we will get this element. So one modulus of the one element is bounded by the modulus of the all supremum of all these quantities. So this can be rewritten, and this is nothing but the norm of alpha norm of f. Okay, so we will establish that f of x mod less than equal to f alpha norm for all x belongs to 0 1, and from there then we will take the supremum of x belongs to 0 1, then we will establish that supremum norm of f is less than equal to f alpha norm. Okay, let us name it equation 1. Okay, so this implies f is all previously we have established that f is continuous, and now it is also this quantity is finite. We have taken that it implies sup norm of f is finite. This implies f belongs to C01 with respect to the sup norm. Okay, with respect to the sup norm. So we established C alpha 01 with respect to the alpha norm, with respect to what norm? Alpha norm. Alpha norm is a subset of C01. Okay, and this is with respect to sup norm. Okay, now we will check that the map T mapping from this is a bounded linear map. Okay, now we will check the option D. T is a mapping from C alpha with respect to the alpha norm to C01 with respect to the sup norm, and this mapping is defined by this way: T of f is equal to f. Claim is that T is a bounded linear map. How? Because linearity is easy, because T of alpha, if we want check T of alpha 1 f1 plus alpha 2 f2, then by using the identity map alpha 1 f1 plus alpha 2 f2, and this is nothing but the alpha 1 tf1, because it is identity map alpha 2 tf2. So this is clear, because it is a linear map, linear and the identity map, therefore it is a linear one. Okay, to show the boundedness we have to verify that prove that T of f norm with respect to the y norm. Here y is the with respect to this is a domain and this is the codomain. With respect to the codomain norm, here the codomain norm is supremum norm. Okay, supremum norm, this thing should less than equal to c times s is independent of f, independent of this should be less than equal to f norm with respect to the x domain norm is alpha norm. This should be alpha, and by the definition of what? By the definition of T, it is identity map. This should be equal to this less than equal to c times f alpha norm. But this thing has already been established. This follows this 2 follows from what? This 2 follows from the 1, because we have already established f sup norm of f is less than equal to alpha norm of f, with when here the constant c is 1. Okay, this c is equal to 1, and it follows from 2. This implies that our function t is a bounded linear map. Let us verify the option. Here in the option D, it is showing that it is not a bounded linear map, so it is false one. Now we will check that whether the image of T is closed in C01 or dense or C01 or not. Okay. But our T is a identity map, so the image of T is equal to the domain of T. So image of T is equal to the domain of T, and the domain is C alpha. This is C alpha. Okay. So we'll check that whether C alpha is dense in C01 or closed in C01 or not. Okay. Let us verify it. Claim check C alpha 01 01 closed in C01, closed in C01. This is asking, and C alpha 01 is dense in C01. We have to verify these two things. Okay. Here one thing is to note that these two things can be verified simultaneously. But before going to verify, let me prove some auxiliary result. Let me verify that P01. Okay, P01. What is P01? It is the space of polynomial functions. Polynomial functions. Space of polynomial functions in 01. Okay. Domain is 01. Okay. Claim P01 is a subset of C alpha 01 subset of means this P01 with respect to the norm alpha norm is subset of this with respect to the alpha norm, not alpha norm. P01 is with respect to the sup norm. P01 with respect to sup norm is a subset of this with respect to the alpha norm. Okay. Let us verify these things. Means one type of every polynomial function is a order continuous function. Let us verify these things. How it will help us to verify this denseness and these things? Means our strategy is to apply the Weirstrass approximation theorem, because polynomial functions are always associated with the Weirstrass approximation theorem. I hope that everyone is well known about the result that the spaces of the polynomial functions is dense in the continuous function space with respect to the sup norm. We will apply the Weirstrass approximation theorem. Weirstrass approximation theorem. Okay, we will apply this theorem, and this theorem says that P01 with respect to sup norm is dense, means its closure is equal to C01 with respect to the sup norm. If I will establish that this is if I will establish that P01 is subset with C alpha 01, and I have already proved that this is also a subset of this one, then I will take the closure, and this is nothing but the C01, so its closure is also equal to this one, means C alpha 01 closure with respect to, here I will closure will be taken on the larger space with respect to the sup norm. Okay, larger space is sup norm. This is equal to C01 with respect to the sup norm. Then our claim is proved. Then we are done. Means in the sense that it shows that C alpha 01 is dense in C01 with respect to the sup norm, and we have already previously told that C alpha 01 is not equal to with C01. Okay. But if this set were closed, then this should equal with the same space. If x is closed, then x closure equal to x, then implies x is closed, if and only if x is closed. But here this is not happening. Here the closure is coming something different, and this space is not equal to C alpha 0 1. So it implies that this space is not closed with respect to the sup norm. Okay, means if we will establish our claim, then we will verify these two options that image of T is closed. This is not true, because image of T will comes its closure will come to the C01, so it is not true. Okay, and image of T is dense in C01. It is true by the Weirstrass approximation theorem. But before that, we have to show that this C alpha contains all the polynomial function. Okay, we will establish it by using the real analysis technique tools, and it is easy. Let us take a polynomial function. Claim is that our claim is P01 with respect to sup norm is subset of C alpha with respect to the alpha norm. Okay, we will prove this one. Okay, how can we prove it? Let f belongs to P01 in this space P01 with respect to the sup norm. We are taking f. Okay, then it implies that sup norm of f is finite. Okay, and f is a polynomial. It implies derivative of f dash is also polynomial. So implies f dash is also a continuous function. It implies supremum of f dash x belongs to 0 1. Okay, f dash x belongs to 0 1 is what? Is finite, bounded, because it f dash is also polynomial. It means f dash is also continuous function, and continuous function on a closed interval is bounded. This implies sup norm of f dash is also finite, bounded by some constant Cf. Okay, Cf is greater than 0. Okay, now we will check this f of x minus f of y divided by x minus y modulus. By using the mean value theorem, this is equal to f dash xi. Don't take the modulus. Before taking the modulus, we can establish this f of x x minus it will be clear. This quantity is equal to with f dash xi by using mean value theorem. For some xi belongs to x comma y open interval. Without loss of generality, you can take x is less than y. Okay, because x not equal to y, here x not equal to y, so one can take x is greater than y or y is greater than x. Okay, then we will take the modulus, and this can be dominated by this one, f of x minus f of y modulus divided by x minus y modulus is equal to f dash xi modulus, and this is bounded by f dash sup norm, infinity norm, which is bounded by Cf. Okay, then we will take the supremum, and here x and y belongs to 0 1. One can take x belongs to 0 1 closed interval. Then you can take supremum of this quantity, supremum of x comma y belongs to 0 1, and x is not equal to y, then f of x minus f of y mod divided by x minus y mod is less than equal to Cf. Okay, this implies that f of 0 plus this quantity here is less than equal to Cf norm. Cf plus f of 0, we are adding f of 0 modulus f of 0 on both sides, and this quantity is nothing but f of alpha norm. F of alpha norm is less than equal to some constant. This implies f belongs to C alpha 01. Okay, we have proved this thing. We have proved that f lie in this order continuous function space, so it contains all the polynomial functions, and we know that polynomial functions are dense in the C01 space, so this C alpha space is also dense in the C01 space. Therefore we have verified the option B and C. Now we will verify whether it is a compact linear map or not. The identity map is compact or not. In this part we will apply the Arzella-Ascoli theorem. Arzella-Ascoli theorem will verify. We are checking that T is mapping from C alpha to C01. Okay, here it is associated with the sup norm, and here it is associated with the alpha norm. This space and this space, and TF is equal to F is compact or not. Is here the T is compact or not. We claim that T is compact. Claim T is compact. Compact means what? Compact means T of S closure is relatively compact, and T of S closure is compact for every bounded set. Bounded means uniformly bounded. Every uniformly bounded set S in C alpha with respect to the norm alpha. Means if you would take a set S which is bounded means it is uniformly bounded, then the closure of the image set is compact in space what? In C01 with respect to the sup norm. Okay, we have to verify these things. This can be verified by using Arzella-Ascoli theorem. Arzella-Ascoli theorem means we will show that Arzella-Ascoli theorem says that if we show that this is compact, this is closure compact means T of S is relatively compact. Okay, means its closure is compact in C01. How we will verify this thing? And S is bounded, so we will take a general bounded set in C alpha. Proof will proceed like this. Proof is proceed like this. Let S is a bounded set, bounded subset of C alpha. Means f of there exists a constant, there exists a constant C greater than 0 such that what? F of alpha norm is less than C for all f belongs to S. This is given. Okay, now our claim and this is nothing but what? This is nothing but f of 0 modulus plus f of S minus f of t supremum of s not equal to t, s t belongs to 0 1, f of s minus f of t modulus divided by s minus t modulus less than c. Okay, and here main point is for all f belongs to s. This is the thing. Okay, and from this we can conclude that we can conclude that fs minus ft mod here, I forgot one thing here, it is alpha is mod less than equal to c times s minus t alpha. Okay, for all f belongs to s, and it is independent of f, independent of f. And this here interesting thing is that this constant c is independent of f, and this s minus t whole to the power alpha is there, and it is for all the f belongs to s. This implies this implies this set s is continuous because equicontinuous definition is what? Equicontinuous definition is for given epsilon greater than 0, we can find a delta greater than 0 such that f of s minus f of t modulus less than epsilon for all s comma t belongs to for all f belongs to s such that s minus t modulus less than delta. Because here our c is independent of f, we can simply take this less than epsilon, then we will calculate that our delta is nothing but epsilon to the power 1 by alpha. Then it works for the all f, because this inequality is for the all f. So this implies that our set s is equicontinuous. Okay, till now we proved that s is equicontinuous. Okay, but our main goal is to show that ts closure which is equal to s closure. Why? Because t is identity, t is an identity map. Okay, therefore ts is nothing but s, and ts closure is s closure. Means in one way we have to show that this is compact. S closure is compact means s is relatively compact, but where? In the range set, means in the it is y space, means our codomain space is C01 with respect to the supernum. Okay, we have to show this one, but our s is bounded, uniformly bounded. Our s is what? Uniformly bounded with respect to alpha norm, with respect to the norm alpha. But we have shown that f of infinite norm in the previous results means where if you go upward, here means here in the equation 1 we have shown this sup norm is dominated by alpha norm. Okay, means sup norm is less than equal to f of alpha norm. We have proved this one. So this is also bounded by C sum, because this space, this set S is uniformly bounded with respect to the alpha norm. Okay, this implies S is bounded, uniformly bounded S is uniformly bounded and equicontinuous. Continuous. It is bounded with respect to supernum. Okay. Now we are in the right position to apply the Arzella-Ascoli theorem, but our main target is to show that S is relatively compact, and its equivalent definition is to show S is relatively compact. We will take any sequence Fn, any sequence n greater than equal to 1 Fn, which lie in the sets S, and show that this sequence has a convergent subsequence. Then you are done. And this sequence has a convergent subsequence. It follows directly because these sequences are lie in S, and S is uniformly bounded with respect to the supernum F. So this sequence is uniformly bounded. Okay. And this all the functions in this sets S are equicontinuous. We have already proved. Therefore, all the functions in this spaces in the sequence Fn are also equicontinuous. These two things combinedly imply that this imply Fn n greater than equal to 1 has a uniformly convergent subsequence. This comes from sequence by Arzella-Ascoli theorem. Okay. This implies what? This implies S is relatively compact. Compact where? Compact in C01. Implies S closure, which is nothing but TS closure, is compact. Compact in C01. Implies T is a compact operator because S is arbitrary bounded set, compact operator in C alpha operator. Okay, we have proved that T is a compact operator. Now we completely finished the question. Means T is a compact linear operator. It is true. Option A is true. Option B is false, and option D is false. A and C are true. Okay. I hope that you all understood it very well. I hope to see you again very soon. Thank you all for your time.